Hello folks, this is Tom from anti-proton.com, and today I wish to talk to you about the basics of how to use a Geiger counter. This is a Geiger counter. As you can see, it's a small device. Before we talk anymore, let's first plug some sound up to the Geiger counter. I use an external sounder. Basically a single speaker. Geiger counters, of course, like mine, have built-in speakers, as you can hear, but I prefer the external speaker better, or more, because it makes a louder sound. I like the louder sound. Hear it? Geiger counters, the operative word here is counter, are devices which use something called a Geiger tube, which is a small gas-filled tube which is used to detect radiation and count it. Geiger tubes are capable of counting and detecting radiation because of an interesting set of properties involving radiation and electrons, which I'll discuss in a moment. First off, let's look at the inside of a Geiger tube and how it works. Geiger tubes are metallic tubes that are full of a very low pressure gas, usually neon gas or something like that, which is reactive to radiation, electrically speaking. The outside of the tube is metallic usually, and negatively charged, with an inner filament going down the inside, which is usually very positively charged. Inside is a gas, maybe 1/10 of an atmosphere, very low pressure. In between these, there is electromagnetic field, and the reason the field exists is because the difference between these is 400 to 500 volts, sometimes up to 1,000 volts, depending on the type of Geiger counter used. If you're more interested in Geiger counters and the insides and how they work, you should look up Geiger plateaus and quenching and halogen Geiger tubes, but we won't cover those for right this moment. In the most basic of sense, when a radioactive burst of energy flows into the Geiger tube, it causes something called an electron avalanche. I can't see very well. Electron avalanche. The electron avalanche occurs when a single atom is struck by a radioactive beam or ray or particle. This knocks off an electron that has an incredibly large amount of energy. As it flows along, it is capable of bumping other electrons and disturbing other electrons and releasing them as well, each one of them containing additional energy. They are accelerated by the difference in potential towards the positive charge, where the ionized atoms, which are positively charged, are then accelerated towards the negative, and they move away from one another. This builds like a cascade, like an out-of-control reaction, until a single pulse of current flies down through the tube into the detecting circuitry. So one pulse of radiation, one piece, one alpha particle, one beta particle, one gamma ray, can produce one single pulse of radiation. This is how a Geiger tube works. Now you hear a tick on my Geiger tube, you are hearing a single event. This is the Geiger tube, this little hole right here. I have, let me see if I can focus in on that a little bit. I have what's called a thin window Geiger tube. See the little window right there? Thin mica window. The tube is a very small thing. The thin mica window would mean that the end of one of these tubes has been made of a very thin material, and the reason for this is that some radiation is so weak that it's not able to penetrate without there being a window. Before I go any further, I should discuss the different types of radiation. I put out a video series, which this is a part of, which discusses alpha, beta, gamma, and even X-rays, but I'll give you one little tiny quick rundown on them right now. Alpha rays are 2 protons and 2 neutrons. They're like the inside of a helium atom, if you like, without electrons. They're very positively charged, having no electrons, and they move through air pretty fast. As deadly and powerful as they are, a single sheet of paper can block one. Beta particles are energetic electrons or positrons. They're smaller, less dense, less mass to them, and they're very negatively charged. They can pass through that same sheet of paper, but a piece of aluminum that's decently thick will stop them. A gamma ray is like a beam of light almost, but incredibly short wavelength, very high frequency, passing through the paper like it was nothing in the aluminum too, mostly stopping in thick lead or heavy cement, but still some will make it through. It's very difficult to stop gamma. That is a basic rundown on your radioactive sources. I should note that X-ray is equivalent to a gamma ray in almost all ways. Not technically exactly, but close enough. While we'll be getting into in a moment the methods of actually using a Geiger counter, first let's talk about why one should even own a Geiger counter. First and foremost, one problem with Geiger counters is that they cost a lot of money. Here's $400. This $400 would pay for my Geiger counter, but not too much more. So why shell out the money? They're almost impossible to get a hold of right this moment after the various things that have happened around the world. Well, let's find out why. As you can see, my current reading, and we'll talk about what these numbers mean in a minute, my current reading is around the 9 to maybe 15 mark, somewhere in there. So just use that as a basic understanding. Think of it like a baseline. In a few minutes I'll explain to you what that actually means and why that's significant, but just understand that 14 is my average in this house, that number. Here, for example, is a piece of radioactive granite. This will be your countertop. This is something you would serve food on. And as you can see, the number is significantly higher than 14. Just think about, serving food on this, parties, putting the baby up here and changing their diaper. Nice, clean, safe, wholesome fun. It's too bad it's not enough radiation to kill the bacteria for you, but regardless, this is a granite countertop. As you can see, radiation is detected. And before anyone asks, the radiation I'm detecting right now has absolutely nothing to do with radon. I keep getting asked that whenever people see granite, they ask about radon. Radon, I should point out, is a gas, a radioactive gas which can be emitted at certain points from certain radioactive elements. And this may actually be emitting some radon, but the levels it's emitting would not be detectable, not with this apparatus, not in this way. It would have to be collected and then eventually tested later on. Notice we're almost up to 30. 30 counts. And remember I said a Geiger counter counts. Well, one of the most simplest ways to count is in counts per minute. 27 counts per minute. What that's telling me is the Geiger counter is approximating that at the current rate it's reading, that's how many counts it would get in 1 minute. I'll talk about averaging in a little bit. First, let me talk about some common household items that you might find that are radioactive. First, there's your granite countertop. Let's move that out of the way for a second and bring in some other things. Everyone knows I like light salt. Light salt is, of course, radioactive. Why? Because it contains, if you can read this or not, but it contains potassium. Potassium contains a naturally radioactive version of potassium. Not all potassium is radioactive, only a little bit of it. And salt in general is not usually radioactive, but light sodium-free salt is often going to be radioactive. And the reason that it's radioactive is because it contains potassium-40. Here is potassium chloride salt. As you can see, it comes in a nice crystalline form. And I have it in a bag. And this is basically the same thing as this. Oops. Let's see what we get off of this. Again, a pretty good reading. Pretty similar to the granite countertop, maybe a little higher. And if we expose this little front window, so the front window I told you about right here is what's pointing at the potassium salt, we may get an even higher reading. And maybe not, we'll stick it back with the way it was. Alright, other household common items you could find. Mine turned out not to be, but many are. Kitty litter. Oops. Kitty litter can be quite radioactive. Mine is not. But the reason it can be is because of clay. Clay that you find out on the ground sometimes is radioactive. Not always, but sometimes. So this is another reason you can find some radiation. Vitamins and minerals. I will not show the front of this bottle, for legal reasons and such. Let us just say that I found online a bottle of a particular mineral supplement which actually contains, according to the ingredients list, thorium. Why you would put thorium in a mineral supplement, I couldn't imagine in my entire life. There's also molybdenum and God, so many other random things. What else was in here? Oh my God, tellurium, yttrium. Well, anyway, I won't say what it is for legal reasons, but very interesting. And of course, soil samples. I took soil samples recently with the radioactive rain that I've been detecting, and I've been testing the soil samples to see what I get off of them. Of course, you can't consider what you see on here to be accurate because I'm surrounded by radioactive objects, so that kind of kills that for authenticity. There's other interesting reasons to own a Geiger counter. If you are a rock and mineral collector like me, then perhaps you should check to make sure all your rocks and minerals are safe. Alright, as you can see, we have a series of rocks and minerals. As you all know, I like rocks and minerals. Which ones of these are radioactive? I have meteorite, potassium chloride crystals, this odd little guy right here. It's green, must be radioactive, right? This big white piece of limestoney looking stuff. This guy straight out of Arizona. And this ugly little rock. Something's ticking. Let's see what it is. I'm holding my speaker. Let's test each one of our items. First off, we let our Geiger counter drop, holding it away until it calms down a bit. And test the rock. You get random ticks every now and then, but they don't necessarily mean anything. Let's hold it over top of these rocks. They tick a little. Why? Because it's potassium chloride, radioactive substance. This guy right here, in fact, we should definitely move rocks away. We know that this is radioactive. We know this is not. Let's divide our rocks away from one another so that they're not contaminating one another's readings. The readings are falling in this. You still get background radiation, which we'll go into in a minute, but not much. Another false alarm. Again, I already know which ones of these are radioactive, so I won't spend very long. Nothing much. A tick doesn't necessarily mean radioactivity. What about you? Anything? Tick, tick, tick? Nothing? Another false alarm. What about this ugly little rock right here? Wait a minute. What are we getting here? Oh no. Couldn't be radiation, could it? Yes, sirree. It is. Here, let's put this guy right here where it can run. As you can see, this little tiny rock right here is radioactive. I've yet to 100% identify what's in it. The point of this whole little adventure is to show you that various household items, your rock collection, antiques, they can be radioactive, and the radiation that is emitted from them can be harmful. In this case, probably not very harmful, but it could be, depending on what it is. If this had been a sample of uranium ore that your uncle had gotten when he was a child and didn't know any better, he could be putting off 4,000 or 5,000 counts per minute, something you wouldn't want to leave in the family living room where the children are. Now let's talk a little bit about how to use a Geiger counter and what some of these little numbers and things mean. It might be time for a little tiny bit of math. Alrighty, radiation can be detected by a Geiger counter, and when it is detected you hear a clicking sound, a count. Notice currently my Geiger counter is counting now. Every single tick it gets, it counts. And it will do this for the next 3 minutes. To get an average for how much radiation you find in an area, you place your Geiger counter beside either what you're detecting or in a general area if that's what you want, and you set the Geiger counter to detect radiation for a certain amount of time. Then you divide the number of counts you get by the number of minutes. Example, let us say that you place the Geiger counter in your living room and you ran it for 1 hour. 1 hour. Now, 1 hour, as you know, equals 60 minutes. 60 minutes. We like to use something called counts per minute, which is the number of counts you get in 1 minute. In order to get an average of this, we need to deal in minutes. Minute, 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 minute. You get the point, right? So when you do things for an hour, 2 hours, 3 hours, convert them to minutes. 2 hours is 120. 4 hours is 240 minutes. You know how to do math, right? That's pretty simple. So 60 minutes. Let us get rid of this now. Let us say that in 60 minutes you detected 1,200, we'll use a C here to mean counts, 1,200 counts in 60 minutes. Alright? Do some really simple math here. That would be 120 counts every 6 minutes, right? Alright. That's 60 every 3. That's 20 every 1. So that's 20 counts per minute. Remember, when doing math and physics, and I know you're not trying to do math and physics, I'm trying to be simple here, but just a little simple rule. When you're doing math and physics, you can actually multiply, subtract, and divide, and whatever the well, not really those, but you can multiply and divide the units. See? 20 counts per minute is what you got. How do I know this is true? Because if I take 20 and multiply it by 60, I'll get 120. Now, this is now the average for the room. We have run this Geiger counter for an hour, and in 1 minute it got 30 counts, the next minute it got 10 counts, and so on and so forth, but the counts all averaged out to a number over time. And like any average, the longer you run it, the more accurate it gets. Ooh, look, we're done. Okay. Now let's do some math here. Let me erase what I've done. I got 138 counts in 3 minutes. Alrighty. Let's figure out what that is. Now I'm going to pause and use a calculator because I'm too lazy to do it in my head. Alrighty, I'm back, and as you can see, I did the math quickly using a calculator because I'm lazy. 138 counts in 3 minutes is equal to 46 counts a minute. And as you look closely, we're at 48 right this moment. It goes up and down, but that's not too far away from what my instantaneous figure is. The instantaneous figure is good to give you a simple, quick idea, but it is no replacement for using a long time count. See, look, we just jumped up to 51 or 52, but it won't be like that all the time. Given time, this will drop down. Now, if we had run this for an hour or two, then we might have gotten an even more accurate response. Anyhow, when taking a Geiger counter, when buying a Geiger counter, the first thing you should do is place it in your house in one single nice safe spot that isn't very high, seemingly. Walk around. Here, I'll show you. Walk around your room very carefully, and you can never be too slow. Don't go near things that are radioactive because they're going to throw off your readings. So go find a place that's pretty safe, put it down, set your Geiger counter for a timed count. In my case, you do it like this. Different Geiger counters have different times. Mine's set for 2 hours, 120 minutes. Then you start the timed count, and you let it run. And then when you're done with this, you'll take this number and write it down. And then you go to another place in your house, and another, and another, and do this in 4 or 5 places in your house. And then you have different averages for the house, because there's different radioactivities in different places. If you want, you can even add them all up and divide them by the number of places you sampled to get an average. You might consider doing this during the day and doing it at night to get an average in each time, because the day and night will have different radioactivities. Only once you know what your average activity is do you understand truly how radioactive something is. Example being, for me, I'm 14 counts per minute, but if I lived in a place that was perhaps 30 counts per minute normally, then 40 counts per minute is only really only really 10 counts per minute. Let me explain that to you a little bit. Maybe perhaps you might want to know something about background radiation. We live on the planet Earth. See, little continents and things that I can't draw. Out in space, out in space you have planets, and you have stars. God, I can't draw. But anyway, radiation comes from these sources. Well, maybe not so much from planets, but definitely from stars and other places. The radiation hits us on Earth. Also, there's natural radiation in rocks, and even sometimes in the air that we breathe. This is what's called background radiation. Background radiation will affect you no matter where you are. Even if you're deep underground, you sometimes pick it up a little bit. The average background radiation is most widely affected by altitude. The higher you are in the air, the more radiation you get. While flying on an airplane, you may receive 300 or 400 counts per minute, whereas here at 50 feet above sea level, I receive about 10 to 15 counts per minute. Let us say that I do an average and find that a room is generally 14 counts per minute. Let us say then I test a cup. Here's a cup. I test the cup with the Geiger counter. There's the Geiger counter. And let us say that I receive a large number and I divide it out, like I said, by the minutes, and I come up with 100 counts per minute. To determine how radioactive the cup is, I need to take my 14 counts per minute, my background radiation, and I need to subtract it from this 100, right? So, reading minus background equals the answer. So 100 minus 14 would be 90 is 86, right? 86 counts per minute is the real radioactivity of this object. It's not this, because it's this plus the background radiation. You understand? And so that's why you need to know what the radiation is around you before you can guess. By the way, notice I'm up to 63 counts per minute. The 63 counts per minute I'm detecting right here. Oh no, I'm counting. Sorry, I'm foolish. Let me switch back. See, I'm down to 14. You can trick yourself too. Be careful not to give yourself a panic attack just because you got the wrong thing. Alright. Notice, by the way, if you look closely, I'm not actually touching the source to the window. Never, ever, ever touch a radioactive source to the Geiger counter's window. It's even worse if you have one of the very large windows in the bottom of some of the Geiger counters, because this can contaminate the window, thus permanently contaminating your Geiger counter, making it basically useless. Alrighty. Next thing we need to talk about is unit conversions. Calibration and unit conversions work about like this. Let us say that I have a rock here and it is a source sample that's been scientifically approved, and many scientists have worked days and nights to figure it out. And they know that at this exact distance, with this exact type of tube, every single count is equal to a particular reading in milliroentgens or microsieverts. Let me switch, by the way, to milliroentgens to show you. Milliroentgens. It's another unit of measure. Oops, can't see because of the light reflecting from my lamp. There we go. See, if you look closely, I'm at 0.027 milliroentgens per hour. If you were to put your Geiger counter and test it and know for a fact that 1 count per minute is equal to 0.01 milliroentgens per hour, meaning that if I receive a continuous 1 count per minute every minute for 60 minutes, then I will have received 0.01 1,000th of a Roentgen per hour. Roentgen is a particular measure of radioactivity. Then I am now calibrated for this particular radioactive source. However, if I put in a different radioactive source, one I don't know the information about, one that perhaps produces more or even less radiation, see? If I put in this other one, I'm still detecting radiation. But here's the question. Is 1 count really equal exactly to this? What if it is equal to 10 times this, 0.1? Then when I think I'm reading this low level, I could be reading a much higher level and not realize it. This is the reason that using millirems and milliroentgens and microsieverts is very, very, very troublesome when doing math with a Geiger counter. It is a general fact that 0.01 milliroentgen per hour is equal to 0.1 microseivert per hour. This is a true statement, but it's not necessarily true that 1 count per minute is equal to either of those in any conceivable way, or any number of counts per minute. That is based on your Geiger counter. Example, my Geiger counter, like most Geiger counters, is calibrated for cesium-137, gamma only. That means that at a certain distance, perhaps maybe 1 meter, with a cesium-137 source, reading only the gamma, meaning I'm shielding for beta, so that means I have something up. Remember the aluminum foil, aluminum, for example, that blocks beta? So I'm only looking at alpha. Not alpha, gamma. I know for a fact that my counts equal, my milliroentgens equal this. Let me put it to you like this. Let us pretend I do not have a cesium-137 check source, but pretend that that's what this is. Here it is on my table. I'm crazy enough to stand here right beside it. And I know that at this distance, we'll say that this is 1 meter. We'll just pretend that it is. That at 1 meter, when I get 16 counts per minute, or 15, I'm getting 0.015 milliroentgens per hour. I know this to be true, because I'm calibrated for this source. I'm calibrated for it. But that means they got it to this point and they adjusted this thing until it read exactly what they knew it should read. Problem: if I go back a distance, then I might not be getting the same amount of exposure. Or, if this changes from cesium-137 to uranium-238, are you absolutely sure this is going to be equal? Probably not. Whereas I may read 11 counts per minute, in reality I may be receiving 0.511 or something to that effect. That's why it's very, very, very troublesome to use milliroentgens or microsieverts, conversely, which is another unit this is capable of using. If I were you and using a Geiger counter, if you don't understand what a microsievert is, or a millirem or a milliroentgen, if you're not clear on those, then A, you should watch my video about the subject which explains it, and B, you should probably just stick to counts per minute. All you need to know is counts per minute and what your average background is, and you're pretty well set for using a Geiger counter. Okay. Now, I've talked to you a little bit about radiation, and I've talked to you about types of radiation, alpha, beta, and gamma, and what stops them and what doesn't. Let's see some examples with real radioactive items. Alrighty, let us now test and see how we may or may not stop radioactivity with something a little more radioactive. First off, the case. I usually keep this behind a little bit more than that. There's definitely something radioactive inside of there. What could it be? The case is doing an okay job of stopping it. We're only being exposed to gamma right this moment. Oops. Well, looky here. If it isn't a depression era glass plate. Hello, depression era glass plate. Yes, sir. The depression era glass plate, as you can see, is very, very beautiful and also very radioactive. Mine, for whatever reason, doesn't do a very good job of glowing when you hit it with black light, like some do, but oh well, it's nice nonetheless. As specimens go, there are significantly more radioactive pieces than mine. Let's move the Geiger counter around a little bit here and place this straight down on it. When I get incredibly close, I'm picking up alpha particles. Those are mostly alpha particles. This is produced by the uranium. Now, I think I might be able to convince you that a piece of paper can stop most of that. The problem is that when I show this to you, some of the radiation you're going to see is gamma. And we want to make sure that you're seeing it truly being blocked. It's actually still gaining on the Geiger counter, so we'll give it another second here to gain. Alright, now let's see what happens when we introduce some paper. Give it another couple seconds to gain. Alright, there it falls off at about 60. So let's put in a piece of cardboard. You're still going to get quite a read off of it because you're getting gamma, but a lot of the alpha should be blocked. Notice the rate is falling. It's still high, don't get me wrong. That's gamma, a lot of gamma. But notice it's no longer up in the 60 range. The plate is still there. If I move, see we're down to 39 and falling. That's because alpha is stopped by paper. However, if I move the paper out of the way and put this back down here again, we should rise back up in just a few seconds to the appropriate level of 60 plus counts per minute. Alrighty. There it goes, it's climbing back up again. I don't have a very strong piece of glass, which is fine with me. I personally don't like being irradiated. Now, let's see what else we can do to stop this radiation. Because other things can block radiation, like I said earlier. First and foremost, here's a piece of 0.019 inch aluminum. See? Let's move this out of the way and put the aluminum over top. There's no more alpha, and let's see if the aluminum blocks any of the gamma. Aluminum is blocking the gamma quite well. It still gets through, but not like it was. We are truly picking up nothing but alpha right now. Okay. Now, what about a sheet of, let's see what I have here. Sheet of 22 gauge steel. remove this. Get rid of the aluminum. But the 22 gauge steel in place. It's all rusty. It's been outside. There's the window right up on it. 25 counts per minute. 27. 24. Notice that the thicker steel made very little difference, and the reason is that it's very hard to block alpha. And now that we've gotten it down this far, not alpha, I'm sorry, gamma. It's very hard to stop gamma. Now that we've gotten it down this far, though, we're still picking it up. We are still picking it up, even through the steel. To tell you the truth, I think aluminum might have done a better job. Let's move this out of the way. Let's try a significantly thicker piece of metal. This piece of metal is, let's see here, 1/4 inch thick. That's a hefty piece of metal. There we go. 1/4 inch thick. Let me get the plate right over top. There. Now we are seriously putting some steel in between us and that. And yet, we will still get reading. It goes right through the steel because it's gamma. Gamma is very powerful. It is not as dangerous as alpha. The alpha that comes from the glass is actually more dangerous, but the alpha can't even penetrate my skin. That gamma can. This is only a few counts above my natural background radiation, which is 14. Pretty nice, huh? That steel really cuts down. Let's try something else. Move that out of the way. Let us move the Geiger counter significantly out of the way. Let us take this large piece of concrete. Hold on, let me put this down for a second. Ugh. There. A large piece of concrete. Now let me prove to you the plate is still in there. I don't know if you can see it or not, but it is still underneath there. You can see we're picking it up from the side okay. Let's put it on top and see. Now keep in mind that the concrete itself is probably a little bit radioactive. All concrete is. Is that over the plate? Yeah, let me move that a little. There, that should be about right. Concrete does a pretty good job too. Now if I add the concrete and the steel together, I can actually basically stop it. Not bad. Notice I'm blocking it from myself right this moment. Talk about paranoia. Alright. If we put this down like this, we'll expose a little bit more of the actual Geiger tube to the radiation. Let's see if I put the steel under it, if I can block it all. There. Because this is longer now, and remember my tube is shaped like this, so when it's pointed down, less of it was exposed than when it was pointed like this. So it should be getting a higher number now, and as you can see, we're still not able to block it all. And the reason is because what we have is very potent. Now when you put everything radioactive together at the same time, everything from the rock to the plate to the potassium salt, you might get some seriously high numbers. Let's see what we get at this higher rate. It just needs to be done. While we're at it, we'll put a couple extra pieces of potassium right around the tube. There we go, 100 counts per minute. 106. 113. 116. Radiation 121. we are fast enough now for counts per second. Almost, well, 2 counts per second now if you like. Alright. Now, let me give you a little bit more information about how to use a Geiger counter, now that we've all had fun being irradiated. But before that, let's see if we cut the Geiger counter off, how fast we can accumulate radiation. I'll put it on the timer mode, on the accumulator mode, so now it will accumulate counts and tell me how many. It is now counting. It is not counts per minute anymore, folks, now. It is just counting the number of counts it gets in a period of time. Like, for example, this amount of time. Being on top of a uranium oxide filled plate, potassium salt bag, and I still think that might be thorium rock. It counts pretty fast. And this is the kind of things we get exposed to on a daily basis, especially if you play around with this stuff. I should probably point out that it's not necessarily safe to play around with this stuff. Alright, here's a little bit of information while using your Geiger counter. First and foremost, never be alarmed by instantaneous spikes. Your Geiger counter can all of a sudden spike, but then return to normal again, and that does not mean that anything bad has happened. When you move your Geiger counter around, it will have a tendency to tick all of a sudden. Same as when you breathe on it, sometimes it will also tick. These are because air moving by causes alpha particles and other such things to get into the actual tube here, or causes other little changes and fluctuations in the capacitance of the air around you. They do not necessarily mean that you're near a radioactive item. On the flip side, you could be near a radioactive item and not be able to pick it up. Like, for example, the thorium rock is inside of this shielded container. It's just simple aluminum, but it's a good enough shield. If I put the Geiger counter right up against the material, it should, right up against the shield, it may actually detect it. Maybe, maybe not. No. Perhaps not. But anyway, so just because you don't detect radiation doesn't mean it's not there. You can never move a Geiger counter too slowly while testing a surface. A good method for testing a surface is to take your hand like this and put your thumb underneath it or your finger so that the two are very close but not touching. I like to do like this. See how I have my fingers? Just making a little platform for it so it doesn't touch. See, no touching. And slowly move. If you think you're getting a tick, sit there for a moment. Wait about 20 seconds and see. If not, keep going. The act of moving itself will cause a tick. But that does not necessarily mean there's radiation. When you do get near something radioactive, hold it there for a few seconds. Let the reading build. The reading will build, slowly counting, until it gets to its maximum level. The maximum level, of course, being the highest it will show you in a given period of time. If you ran a longer statistical count, such as 1 hour divided by 60 minutes, that would also serve the same purpose, showing you a more realistic amount for what's actually there. To give you another little bit of information, you cannot detect some radiation that you know exists. For example, bananas have potassium and emit radiation, yet bananas are perfectly safe and they emit so little radiation that you cannot detect them with this unit. Given maybe perhaps a 24-hour count in an incredibly controlled area, it might be possible, but it's not realistic. A very powerful Geiger counter might be able to detect the radiation in a banana. So there's lots of things that emit radiation you cannot just detect automatically. The rain, for example, from Fukushima. Ooh, look, a quick burst. That burst does not necessarily mean that anything bad has happened, nor does it mean that my hands are radioactive. Putting my fingers near this hopefully will reveal that. Let's move this back. I might be in a perfect geometry with this to pick up. And as you can see, it's dropping. The spike may have had nothing to do with my hand whatsoever. Little spikes like this will appear and they're perfectly fine and normal. When reading counts per minute, remember it's important to do a long running background count, -14 for example. Without such a long running count, there's no way for you to know if you're being exposed to radiation. If I lived in Denver, I could be saying 50 or 60 on this dial and it would be perfectly fine. If I bought a larger, wider pancake tube, one of the really, really big wide ones like this, big circular one, it could be 5-6 times that number. And that would be perfectly safe and normal for that Geiger counter. So just keep this in mind. If you have any questions, if you want to know more about Geiger counters and how to use Geiger counters, please don't hesitate to ask. I will be getting another Geiger counter very soon so I can compare the two and show you more information. I'm considering even rebuilding this entire series at that point. Anyway, this has been Tom from anti-proton.com. Please be safe. Please don't try this at home. Bye-bye.